Welcome to one of the most mind-bending paradoxes in physics, the Poincaré Recurrence Paradox. This paradox reveals a deep tension between the reversible laws of classical mechanics and the irreversible arrow of time we observe every day. Let's start by understanding what Henri Poincaré discovered in the late 1800s. Poincaré proved that in any closed finite system with fixed energy, if you wait long enough, the system will eventually return arbitrarily close to where it started. Mathematically, a closed system with finite phase space, given sufficient time, must experience recurrence. Imagine a particle moving in a circular closed system. Poincaré proved it must eventually return very close to where it started. But here's the puzzle that drove physicists crazy. If this theorem is true, why don't we ever see scrambled eggs unscramble or broken glasses reassemble? Let's use a deck of cards to understand this paradox intuitively. Start with a deck of cards in perfect order, ace through king of each suit. Here's the question. If you shuffle this deck over and over again, literally forever, will it eventually return to the exact original order? According to Poincaré's theorem, the answer is yes. It absolutely must return to the original order eventually. After countless shuffles that scramble the cards, the theorem says they must eventually return to 1, 2, 3, 4, 5. But here's the crucial catch. Exactly how long would we have to wait for this miraculous return? Let's calculate how long we'd actually have to wait for recurrence. For a standard deck of 52 cards, there are 52 factorial different possible arrangements. 52 factorial equals approximately 8.07 times 10 to the power of 67. That's 80 unvigintillion. If we shuffle once per second, we'd need 10 to the 67 seconds, or about 10 to the 60 years. Compare that to the universe's age of only 14 billion years. The recurrence time is incomprehensibly larger than the age of the universe. This is exactly why we never see recurrence in practice. The waiting time is so astronomically large that it's effectively infinite. To understand this more deeply, we need to talk about phase space and microstates. Phase space is the mathematical space containing all possible states that a system can occupy. Each point in phase space represents one possible configuration of the entire system. For a gas, this includes positions and velocities of all molecules. The phase space volume is the product of all position and momentum uncertainties for every particle. For a gas with n particles, the phase space is 6 n-dimensional, 3 position coordinates, and 3 momentum coordinates for each particle. Now let's connect this to entropy and thermodynamics. Entropy is fundamentally a measure of how many different microscopic arrangements correspond to the same macroscopic state. The Boltzmann entropy formula, S equals Kb times the natural logarithm of omega, where omega is the number of microstates. Low entropy means particles are confined to a small region with few possible arrangements. High entropy means they're spread out with many possible arrangements. Here's a crucial question. If the system returns to its initial state through recurrence, doesn't that mean entropy decreases? Answer: yes, entropy would temporarily decrease during recurrence, but only after a time so long it's practically impossible. This brings us to the second law of thermodynamics and its statistical interpretation. The second law states that entropy change must be greater than or equal to 0 for isolated systems. But Poincaré recurrence seems to violate this sacred law. If systems return to low entropy states, how can entropy always increase? As time flows forward like arrows radiating outward, entropy increases almost always. Recurrence is so rare it's negligible. The resolution is that the second law is statistical, not absolute. Entropy almost always increases, but not strictly always. The probability of entropy decrease is proportional to e to the minus delta S over Kb. For macroscopic systems, this is vanishingly small. Let's work through a concrete numerical example with gas molecules in a box. Consider 1 mole of ideal gas, which contains approximately 6 times 10 to the 23 molecules, Avogadro's number. N equals 6.02 times 10 to the 23 molecules. Initially, let's say all molecules are confined to the left half of the box. This is a low entropy state. Here, all the gas molecules start on the left side of the box, a highly ordered low-entropy configuration. Now the question: what's the probability that after the gas spreads throughout the box, it spontaneously returns to all being on the left side? Each molecule has a 1/2 probability of being on the left side, so the total probability is 1/2 to the power of n. This equals approximately 10 to the negative 10 to the 23. This number is so small, it's essentially zero. In equilibrium, molecules spread uniformly throughout the box, maximizing entropy. This is what we actually observe. Let's estimate the actual recurrence time for this gas example. A typical time between molecular collisions is about 10 to the minus 10 seconds, or 1/10 of a nanosecond. We denote the collision time as tau collision, approximately 10 to the minus 10 seconds. The recurrence time is roughly the collision time multiplied by 2 to the power of n, the number of possible states. This gives us approximately 10 to the 10 to the 23 seconds. This is a number so large we can't even comprehend it. Compare this to the heat death of the universe at 10 to the 100 years, the sun's death at 10 billion years, and the universe's current age of 14 billion years. The recurrence time is so incomprehensibly vast that it exceeds any physically meaningful timescale by factors we can't even express. So why isn't this actually a paradox? Let's resolve the apparent contradiction. The key insight is that Poincaré recurrence is mathematically true in principle, but physically irrelevant in practice. There's a gap between mathematical truth and physical reality when timescales vastly exceed the age of the universe. Therefore, the second law of thermodynamics holds for all practical purposes. Entropy will never spontaneously decrease in any system we can observe. This raises a philosophical question. Does this mean our physical laws are somehow incomplete? Answer: no. It simply means we must carefully distinguish between different timescales and recognize when mathematical possibilities become physical impossibilities. Interestingly, quantum mechanics introduces additional complications to this story. In quantum mechanics, phase space is fundamentally discrete rather than continuous, due to Heisenberg's uncertainty principle. The uncertainty principle states that delta x times delta p is greater than or equal to h bar over 2. This means quantum phase space consists of discrete cells, not a continuum, fundamentally changing the nature of recurrence. Quantum mechanics actually makes recurrence times even longer in many cases, reinforcing that we'll never observe it. This paradox continues to have implications for modern physics research. The Poincaré recurrence paradox is directly relevant to the black hole information paradox, where information seems to be lost. It's also relevant to cosmology and questions about the ultimate fate of the universe over infinite time. Black holes pose similar questions. Does information eventually return through Hawking radiation, or is it truly lost forever? Some speculative theories even suggest that our entire universe might experience recurrence over timescales of 10 to the 10 to the 120 years or more. Let's conclude with the profound philosophical implications of this paradox. The arrow of time we experience emerges from statistics and probability, not from fundamental reversible laws of physics. The arrow of time is statistical. Entropy increases because high entropy states are overwhelmingly more numerous than low entropy states. The key lesson is that recurrence is possible in principle, but impossible in practice for any system we'll ever observe. Mathematical principle does not equal physical practice when time scales differ by factors of 10 to the 10 to the 23 or more. Let's summarize how we resolve this paradox. First, Poincaré was absolutely mathematically correct. In a closed finite system, recurrence must eventually occur. Second, the timescale for recurrence is longer than the age of the universe by incomprehensible factors like 10 to the 10 to the 23. Therefore, the second law of thermodynamics holds perfectly for all observable physics. We'll never see entropy spontaneously decrease. When recurrence time vastly exceeds universe time, there's no paradox in practice. Theory and observation align perfectly. This paradox teaches us something profound about the statistical nature of time and the emergence of irreversibility from reversible laws. Finally, it reminds us that mathematical possibility and physical reality can be separated by timescales so vast they might as well be infinite. And that's the beautiful resolution of the Poincaré recurrence paradox, where mathematics, physics, and philosophy meet.